Okay, one thing I wanted to show you and I didn't get to last time is, and this again is probably more practical. This is the one I always use when we have a lab. If I get a lab and it says, I need 500 milliliters of a certain molarity solution, um, how do I make it? Okay, so this is going backwards. All right, so let's say I need to make a solution for lab potassium sulfide, excuse me, and I need 400 milliliters of it, and I need it to be 1.25. So now what I need to do is I need to figure out my grams of K2S. I need to figure out my grams of solute. So if we remember, molarity is moles divided by liters. Well, moles, if you manipulate that formula, is molarity times liters. So if I take this and change it to liters, 0.4, and I multiply by the molarity I want, I'm going to get moles. Okay, so now I know how many moles I need of potassium sulfide. But here's the problem. We don't have a mole meter to measure things out. I have to change it to grams. Well, we've done that a bunch of times in chemistry. All you do is take my 0.5 moles, find the formula mass of K2S, 2 potassium, 1 sulfur, it's 110. And again, if you have that app on your phone, if you don't have that app on your phone, you guys, just look for app. Mine is an Apple one. If you don't have a iPhone, I know that Android has them. It's just you're calculating molar mass. Get that on your phone because it'll help you a lot. Because you type in K2S and you'll get 110 grams. That's what it weighs. So I just multiply the two, so I get 55 grams. So if I want to make this solution, I measure out 55 grams of K2S. I add it to 400 milliliters of water. Once it's mixed, then I know that's what the molarity of the solution is. And honestly, this is more practical than the other way where you get the grams and you get the volume, you got to figure it. Now, in the other ones, you divide by the molar mass and then you divide by the liters. In this one, you do just the opposite. You multiply the two together and then you multiply by the formula mass. And then this, you'll get how many grams you need to add. Okay? All right, the next thing we're going to talk about when you talk about solutions is something called colligative properties. When you have a solution, you have interactions in there between the solute and the solvent. Okay, when you have colligative properties, what happens is you mess with those. Okay, what happens is when you add particles, it's just like when we get a lot of ice and we throw salt on it and it gets rid of the ice. What you're doing is you're messing with the interactions in the water. You're adding the salt particles and it changes things. It changes melting point, it changes boiling point, it changes what they call osmotic pressure. So by adding extra particles, you're messing with the normal interaction of the particles in that solvent and you're changing stuff. It does not matter what you add, it matters how much. It's the number of particles, not what you actually add. Okay? So here's the things that colligative properties affect. Vapor pressure, okay? The pressure at the surface that allows gases to be dissolved in liquids, you mess with that when you add particles. The boiling point and the freezing point, I already measured that. And osmotic pressure. Osmotic pressure is moving, osmosis means movement of water so that you have equal concentrations. Well, and again, I'll show you how to do that. But you mess with that when you add particles, okay? So these are the things that colligative properties affect. And when you work with colligative properties, you work with molality, moles per kilogram solvent, okay? That's what you use. And again, when you're talking about colligative properties, it's not how many or what you add, it's how many particles you add, okay? So here's vapor pressure, okay? Because you have a solute-solvent interaction, the molecules interact, higher concentrations, and when it says non-volatile, this means it doesn't change to a gas easily. You want non-volatile solutes. They make it harder for the solvent to escape. They hold on to it, okay? So basically what they do is they lower the vapor pressure so then it's easier. If you look here we've got these dissolved in a solution and they escape at a certain, rate. Okay, this is at equilibrium. So the dissolving and the, escaping are the same. That's equilibrium. Okay, if you add particles in here, okay, the rate of vaporization is reduced by the non-volatile substances. So what's going to happen here is they kind of hold on to it, and so it doesn't happen as fast. You can see I can dissolve more particles than are released. So I change the equilibrium, and the red ones are the non-volatile. Okay, and then when I get here, eventually it'll get reestablished, but it'll be at a different level. Okay, so vapor pressure is the pressure at the surface, and when you add particles down here, because they change the interaction, they don't escape as easily. They kind of like hold on to them. So it changes that pressure. Okay. In order to figure out vapor pressure, they use something, it's called Renault's law. Okay. The vapor pressure of a volatile solvent, and a volatile solvent would be like your organics, gasoline, things that, remember I said if it's volatile, it has an odor. But anyway, a volatile solvent over the solution is the product of the mole fraction of the solvent times the vapor pressure of the pure solvent. And you're just like, huh? It sounds a lot more complicated than it is. A mole fraction would be the moles of the whatever your solvent is, usually water, over the moles of the solution. We can find that easily. And then you just take that number and you multiply what the normal vapor pressure of it is. Okay, so I'm pretty sure I have here. If it's an ideal solution, in other words, one with low concentrations, it says it'll follow this law, and we're going to just go with that. There can be some interactions that mess it up a little bit, but they're few and far between, so we're not going to worry about them. We're just going to go with, yeah, we're going to follow this law, and I'll show you how to do it. Okay, so we're going to find the vapor pressure of a solution when we have 10 grams of potassium chloride is dissolved in 500 grams of water at 25 degrees Celsius. That's the standard temperature, okay? If it's not listed there, then you'd have to look up what the vapor pressure is, but we're going to go with that. And the vapor pressure of pure water is 23.8 torrs. This is its normal vapor pressure, okay? So what we got to do is we got to find our mole fraction. To do that, we got to find our moles of water. So we take 500 grams of water and we divide by 18 because that's its formula mass. So this is how many moles of water are in here. 27.75. Anybody want a dog toy? Oh, these dice. So anyway, that's how many moles of water we have. Okay, now we got to find the moles of our potassium chloride. It says we have 10 grams. Okay, so 10 grams times, and again, we're going to divide by its formula mass, 74.5. Dog, quit it. That's what one potassium, one chlorine, when you add them together, what it weighs. Okay, so we find our moles here. So we got our moles of our water, and we got our moles of our solute, which is potassium chloride. Now to get our mole fraction, what we do is we take our moles of our solvent, water, 27.75, and then we need our moles of our solution. So what I'm going to do is I'm going to take the moles of the water plus the moles of the solute, because it's the moles of the solvent over moles of solution. So I'm going to have to add these together for the bottom. And I get 0.995. That's my mole fraction. So all I do is I take my mole fraction times the original pressure, and that gives me the new pressure. So what this does is it tells me by adding that 10 grams of potassium chloride to this mixture, what I've done is I've lowered the vapor pressure from 23.8 to 23.68. Not a lot, but really that's not very much that you're adding. Okay, so that's how you do it. You find the mole fraction. You find the moles of the water, and again, just take how much water you have and you divide by 18 because that's its mass. And then you find the moles of your solute, which is in this case 10 grams over 74.5. That's what potassium chloride weighs. And you get this, the water on top, the solvent, and then you add these two together on the bottom and you get this. That's the mole fraction. Then you take that times what the normal vapor pressure of pure water is, and then you get this number. It's going to lower it a little bit. Okay. When we talk about boiling elevation, what happens is when you add solute particles to usually water, it changes the atmospheric pressure, and so the boiling point is raised. When we boil water to make noodles, we put a little salt in it. A lot of times we do that for flavoring, but we're also making the water boil at a higher temperature so it cooks our noodles faster. Okay. So when you add particles to a substance, you're changing the boiling point. Now it has to be hotter in order for it to boil. Oh, another dog toy. Freezing point is the same thing. And the weird thing about it is it affects freezing point more than it affects boiling point. And the reason for that is if you think about it, when it's starting to boil, those particles are kind of moving up really far apart, so they're not as affected as much by interactions as when they're freezing. So it does the same thing though. This is why we put salt on ice. It really doesn't melt the ice. What it does is it interacts with the water, and now it has to be colder for it to freeze. Okay, so it kind of melts the ice, but really what it's doing is it's changing the freezing point. Dan! Sorry. Okay. All right. So whenever you add particles, you change the boiling point. It has to be hotter to boil, and you change the freezing point. It has to be colder to freeze. Okay. When you have a change in temperature, it's directly proportional to the molality. Molality is important. And we use something called the Van de Hoff, and I'll show you that factor in a minute. It's a little bit different. Down here, they show you, you have to use constants. There's constants for boiling and constants for freezing. Now, most commonly, you were going to use water. The constant for boiling is 0.51. The constant for freezing, I'm sorry, I'm kind of in the middle here, is 1.86, okay? So negative, actually. So you can see that freezing is affected much more than boiling. And here's some other common solvents: benzene, ethanol, carbon tetrachloride, whatever. And you can see their numbers there too, okay? So when you add a molecular compound, we don't use what they call the Van de Hoff factor. It's the number of particles. And again, this is for ionic compounds, and I'll show you how to figure that out here in a minute. But the formula to figure it out, the change in boiling, is going to be the, if you look here, I is what they call the Van de Hoff, and I'll show you how to do that. K sub B is this number, and then M is the molality. So really what you do is you take the molality times this constant to figure out how much you're going to change the boiling point. Okay? Freezing is the same thing. You're going to take the molality times the constant for freezing. So the only thing different is the constant. Okay? All right. Find the freezing point depression if 36 grams of carbon dioxide is dissolved in 300 grams of water. Where am I doing? Oh, I'm at 11. Good. I don't want to run out of time. You know I do that all the time. Okay. So the constant for freezing times molality. Well, I got to find molality. 36 grams, change that to moles. Okay? And then divide by 0.3 because remember it's kilograms. So 36 grams of CO2, 1 mole is 44 grams. So that's how many moles I have. 0.82. And all I did was I took 36 grams of CO2 and I divided by its formula mass. And then I take, again, remember it's kilograms, so move it over 3. So I found the molality. Molality is 2.73. All I have to do is one more step. We've already done molality. All you have to do is take molality times the constant for freezing, which is 1.86. And I put a star by it because that's a constant. It's in that chart. It never changes. So now instead of water freezing at 0, it has to be negative 5.08 Celsius. And if you think Celsius, that's probably about 11 degrees, negative 11 Fahrenheit. So it's changed it, okay? It's lowered it. It's interfered with those reactions. So now it has to be colder for it to freeze, okay? And again, this is a constant. It never changes. If you're doing water, you always use negative 1.86, okay? And there's, in your book, there's a table, 13.3. It's on 546 in your book, and it has all the constants for all the solvents. And again, most of the time we use water. Okay, so find the boiling point elevation. Okay, so now we're going to do boiling point. Same deal. Constant for boiling times molality. So find molality. Take 45 grams of phosphorus disulfide, and I'm going to dissolve it in 520 grams of water. So take this, 45, divide by its formula mass, 95, and you get 0.47 moles. Divide by 0.52 kilograms. Now you got your molality. Okay, and then it's just one more step. Multiply by the constant for boiling for water. So now instead of boiling at 100 degrees, it boils at 100.46. Okay, so if I want the change in elevation, that's it. If I want to know the new boiling point, I'd have to add 100 to it because 100 is the normal boiling point. Okay, that's how you do boiling point. And again, the constants are in your book. They don't change. Okay, and again, like I said, the new boiling point would be 100.46. The change is 0.46, but the new boiling point would be 100.46. It's easy when you do freezing because water freezes at 0. So whatever number you get is the actual change and the new freezing point. Okay. All right. How many grams? Where are we at? Oh, we're not going to get to this one because there's only about 30 seconds left. So this is where we'll take off, and then I'll show you again some more colligative property problems. We'll start simple and then we'll get more complicated. Okay. All right. So that's it for this section. We'll continue with colligative properties next time.